My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about the AC dynamo. The dynamo is a device that converts mechanical energy into electrical energy. In this edition, we'll learn about the scientific idea, mode of work of the dynamo. Also, we'll try to obtain a formula that gives the instantaneous EMF induced in the coil of the dynamo. And we'll try to convert it into DC dynamo. So let's get started. AC dynamo. What about the dynamo? It is a device which converts mechanical energy into electrical energy. So talking about energy conversion that occurs in the dynamo, yes, mechanical energy is converted into electrical energy. That's to say, coil of the dynamo is moved so as to obtain electrical energy. Motion is converted into electrical energy. And what about the scientific idea of the AC dynamo? Actually, it is based on electromagnetic induction. So, what about the idea? Scientific idea of the AC dynamo? It is based on electromagnetic induction. As the coil is rotated, sides of the coil cut the magnetic flux and an EMF is induced. And what about the structure of the device? Talking about the structure of the device, it is shown in front of you now. The device has a rectangular coil. So it consists of a rectangular coil. And as I said, it has to be rotated. The coil is rotated in a magnetic field. Between the poles of a permanent magnet, U-shaped permanent magnet. Actually, the ends of the coil, as you see, are connected to two slip rings. And there is something that touches the slip rings. Yes, we call it brushes. So we've got two carbon brushes that press lightly against the slip rings. This was about the structure of the device. Simply, yes, it consists of a rectangular coil which is rotated between the two poles of a permanent magnet. And we've got two rings and two brushes. What about its mode of work? So talking about mode of work of the device, as the coil rotates, its sides, its limbs, cut the magnetic flux lines, and therefore a current is induced in it. A current is induced in the coil. The direction of the induced current can be determined by applying Fleming's right-hand rule to either side of the coil. So if you want to determine the direction of the induced current, all you have to do is to use Fleming's right-hand rule. And now, calculating the EMF induced in the coil of the dynamo. We want to obtain a formula, a relation that gives the EMF induced at any instant inside the coil of the dynamo. Okay, in front of you we've got a coil placed in the vertical position. By the way, vertical position, we call this position zero position because at this particular position, EMF induced in the coil is zero. Sides of the coil, yes, move parallel to the field. Okay, and the coil, yes, it starts motion, rotating, So we've got an angle here, angle theta. So what about theta? Your attention please. Theta is the angle between normal to the plane of the coil and magnetic field. Okay? And also, yes, thank you very much. It is the angle of rotation of the coil starting from the vertical position. I'm talking about theta. Theta is the angle of rotation of the coil starting from the vertical position. And it is the angle between normal to the plane of the coil and magnetic field. Also, it is the angle between, yes, direction of motion of either side and magnetic field. The EMF induced in one side, and we've managed to obtain this before, it is given by the expression minus BLV sine theta. B magnetic flux density, L is the length of the coil, side of the coil, V its linear velocity, theta I explained. What about the angle theta? As I said, yes, it is angle of rotation from the vertical. It is the angle between normal to the plane of the coil and magnetic field, and it is the angle of, yes, direction of either side of the coil and magnetic field. So EMF induced in one side is given by negative BLV sine theta. Negative sign indicates Lenz's rule. V is the linear velocity at which the side moves. Theta is the angle of rotation of the coil starting from the vertical position. Since omega is given from V over R, so linear velocity equals angular velocity omega times R. So the EMF induced in one side can be expressed as follows. It is equal to minus BL, and instead of saying V, yes, omega R sine theta. This is, yes, the induced EMF in one side. For one side, it is minus BL omega R sine theta. For two sides, it is, yes, 2 BL omega R sine theta. Okay, that's for both sides. But the product of 2RL is the face area of the coil. It is area of the coil. So we can say instantaneous EMF induced at any instant in the coil of the dynamo equals minus BA omega sine theta. Yes, this is very true, but for just one term. And it should be equal to NAB omega sine theta for n number of turns. Okay, so we managed to obtain the relation, the expression that gives the instantaneous EMF at any instant inside the coil of the dynamo. It is equal to NAB omega sine theta. N is the number of turns of the coil, turns on the coil of the dynamo. A is the face area of the coil. B, magnetic flux density of the field, yes, in which the coil is rotated. Omega is the angular velocity. Theta is the angle of rotation starting from the vertical position. When the coil rotates from the vertical position through an angle theta, which is equal to 90, when it rotates through an angle 90, okay, it will be in the horizontal position. In the horizontal position, EMF is maximum because sides moves perpendicular to the field. We've got maximum cutting. So when the coil rotates from the vertical position through an angle 90, what happens? The coil becomes in the horizontal position, and its plane is now parallel to the field, and the EMF induces a maximum. Why? Because sides will be moved perpendicular to the field. We'll obtain maximum cutting. So we can say when theta is equal to 90, the instantaneous EMF is then equal to maximum, EMF maximum. So EMF instantaneous equals EMF maximum, and it is equal to NAB omega sine 90. As I said, when it is rotated through an angle 90. Sine 90 is equal to 1. In this way, we've managed to know something. Yes, we managed to know that maximum EMF is just equal to NAB omega. Okay, so EMF maximum is equal to NAB omega. So in general, we can say EMF instantaneous is equal to NAB omega sine theta. And let me remind you, NAB omega is the maximum EMF. Okay, so we can say instantaneous EMF is equal to EMF maximum sine theta. And EMF instantaneous equals EMF maximum sine theta. In details, we can say it is equal to NAB 2 pi f, if it's the frequency, sine. Instead of saying theta, we can say, thank you very much, 2 pi ft. We've got something here important to mention. We've got important hints. Average EMF. What about the average EMF induced in the coil of the dynamo? Actually, it is equal to maximum EMF times 2 over pi. And how to prove this? Okay, stay with me, please. This can be proved as follows. Since EMF maximum is equal to NAB omega, and omega is equal to, yes, 2 pi f. So EMF maximum is equal to, yes, NAB 2 pi f. If it's the frequency, and frequency is the, yes, reciprocal of the periodic time. So EMF maximum equals NAB 2 pi over t. T is the periodic time. Okay, we'll do something here a little bit strange. Yes, numerator and denominator is multiplied by 1 over 4. So 1 over 4 NAB 2 pi over 1 over 4 t. But NAB over t over 4 is the average EMF. NAB over t over 4 is the average EMF, because average EMF can be obtained either by NAB over the time of a quarter of a cycle or 2 NAB over the time of half a cycle. So NAB over t over 4 is the average EMF times 2 pi over 4. So we can say, as I said, EMF average equals NAB over t over 4. So EMF maximum equals EMF average pi over 2. And if we want to start with EMF average, it is equal to EMF maximum 2 over pi. And now talking about factors affecting the magnitude of the EMF generated in the coil of the dynamo. If we want to increase the magnitude of the EMF induced in the coil, we want to increase the size of the EMF induced. Okay, what to do? The factors affecting the magnitude of the EMF, first of all, it is number of turns. Okay, and second factor is magnetic flux density, denoted by beta, area of coil, and the angular velocity with which the coil is rotated, omega, and sine the angle of rotation of the coil starting from the vertical position. Sine the angle of rotation of coil starting from the vertical position. Or we can say cosine the angle of rotation starting from the horizontal position. As a matter of fact, the induced EMF and the induced current can be increased by, so to increase the EMF, and when EMF is increased, the induced current is increased. All you have to do is to, use a coil with more turns. This can be happened by using a coil with more turns, using a stronger magnet, winding the coil on a soft iron armature, rotating the coil at a higher speed. And we've got very important observation here. We've got something here very important to say. The current actually obtained from the AC dynamo is an alternating current. What does it mean? So we want to define alternating current. What about alternating current? Yes, it is shown in front of you. It is an electric current which varies in strength and periodically reverses its direction. This was about the definition of, alternating current. It is an electric current which varies in strength and periodically reverses its direction. We've got something very important. This important thing is called the effective value of the alternating current. What about the effective value of the alternating current? It is the value of the direct current. So I'm defining the effective value of the alternating current. It is the value of the direct current that would produce the same thermal effect, heating effect per second as the alternating current. Okay, so definition of the effective value of the AC current, it is the value of the direct current that would produce the same heating effect per second as the alternating current. As a matter of fact, the expression that gives the effective value in terms of the maximum value is EMF effective is equal to EMF maximum times 0.707. Okay, and also effective value of the current is equal to maximum value times 0.707. 0.707 is sine 45 or cosine 45 or 1 over square root 2. Okay, and now talking about current rectification in the dynamo. Current rectification means converting AC current into DC current. So talking about DC dynamo, current rectification in the dynamo. It is conversion of an alternating current into direct current. We call this rectification. It is conversion of an AC current into DC current. To perform this, to fulfill this purpose, the two metallic rings are replaced with a commutator, as shown in front of you. We don't have any two rings. They are replaced by a commutator. What about the commutator? It is a cylinder split into two halves. Each end of the coil is connected to a cylinder half. Okay, so the two metallic rings are replaced with a commutator. The commutator consists of a hollow metallic cylinder split into two halves which are insulated from each other. And now we've got very important question. What about the function of the commutator in the dynamo? By applying Fleming's right hand on the two sides of the coil during one complete cycle, we find that the commutator reverses the direction of the current. It reverses the direction of the current in the coil each half cycle. So it reverses the direction of the current twice a cycle. Once again, the commutator reverses the direction of the current in the coil each half cycle. So the current in the external circuit flow in one direction. In front of you, we've got a diagram that shows the function of the commutator. As I said, it reverses the direction of the current in the coil each half cycle to make it rotate in one direction. So the coil is rotated, and after rotation through an angle 180, we will obtain the same direction of current in the external circuit. It is shown in front of you that the current in the external circuit flows from brush F2 to the other brush F1, even after the coil is rotated through 180. Okay. The current obtained when using a split ring commutator is unidirectional. Yes, of course, it has just one direction, but still changing, but varying one. Okay. The current obtained when using a split ring, this is very important, commutator is unidirectional but varying one. It is shown in front of you. Okay, it is unidirectional but pulsating current. Each quarter of a cycle it changes from 0 to maximum, okay? Or it changes between maximum and 0. And now obtaining a more steady current from the dynamo. How to obtain a more steady current from the dynamo? It's all easy. All we have to use here, yes, we have to use a set of coils instead of, yes, just one coil. So when the two coils placed at right angles to each other and a commutator of 4 segments are used, such that each coil is connected to its own pair of segments, the current will be roughly at its maximum value, shown in front of you. And finally, a more steady current can be obtained by using many coils at equal angles to one another. So all we have to use is many coils at equal angles to one another. And what about the commutator? What about the segments of the commutator? Number of the segments should be twice the number of the coils, okay? Together with a commutator which has a number of segments twice the number of coils. And now we've got questions. The diagram shows a coil being turned in a uniform magnetic field. This is the coil. Okay. We want you to sketch a diagram to show how the EMF induced in the coil varies with time. Starting from the horizontal position where the EMF induced is maximum. Sketch a diagram to show how the EMF induced in the coil varies with time during one complete cycle, starting from the position shown in the diagram. Starting from the horizontal, so we should start from the, yes, maximum EMF. It is shown. Okay, another part of the question, the coil has 300 turns. Area of coil is 14 centimeters squared and rotates 3000 revolutions per minute. And density of the field is 50 millitesla. What is the maximum EMF induced in the coil? What is the value of the instantaneous EMF induced in the coil after 5 milliseconds from passing the position shown in the figure? From passing the horizontal position. Okay, if we want to sketch the diagram that shows how the EMF induced in the coil changes through one complete cycle starting from the horizontal, it is shown in front of you. We start with EMF maximum, okay? And what about the maximum EMF? Maximum EMF is obtained from the expression NAB to pi f. Number of turns 300, area 14 centimeters squared, so it is multiplied by 10 to the power of -4 times magnetic flux density, which is 50 millitesla, it is multiplied by 10 power -3 to pi. And what about the frequency? 3000 revolution per minute, so it is divided by 60. In this way, we managed to obtain the maximum EMF. It is 6.6 volt. And what about the instantaneous EMF after passing? Yes, after 5 milliseconds from passing the horizontal. Passing the horizontal, we have to use cosine. So it is equal to 6.6 cosine 2 pi ft, 2 times 180, frequency 50 times 5 times 10 power -3, it is 6.6 times cosine 90. Cosine 90 equals 0, so it will be 0. It happens because at this particular instant the coil will be, yes, placed in the vertical position. Another problem, an AC dynamo has a rectangular coil 40 centimeter long and 30 centimeter wide. Okay, this is the dimensions of the coil. Let me say it again. An AC dynamo has a rectangular coil 40 centimeter long and 30 centimeter wide, produces an AC current of frequency 50/11 hertz and an AC voltage with effective value, so the effective value is given to be equal 200 times square root 2 volt. If the number of turns of the coil, turns on the coil, is 300 turn, we want you to calculate the maximum induced EMF in the coil, the magnetic flux density. So we want you to calculate maximum, yes, induced EMF and magnetic flux density. If the coil is rotated about an axis parallel to its length at velocity of 3 meters per second, your attention please, the velocity given to you is linear velocity. It is equal to 3 meters per second. So we'll need to convert it into angular velocity. So if the coil is rotated about an axis parallel to its length at velocity of 3 meters per second, calculate the maximum induced EMF in the coil. First of all, effective value is given. It is equal to EMF maximum times 0.707. So EMF maximum equals EMF effective, which is equal to 200 times square root 2 over 0.707. It is 400 volt. So this was about the maximum EMF. Concerning the first part of the problem, effective value of the EMF is given by EMF maximum times sine 45 or cosine 45, which is equal to 0.707. So maximum EMF equals the value of the effective over 0.707. It is 400 volt. Maximum EMF also is equal to NAB omega. So 400 is equal to, number of turns is 300. We've got 300 turns on the coil. Dimensions are 40 and 30 centimeters. So they are converted into meters. So multiplied by 10 power negative 4 to convert from centimeters squared into meters squared. Beta is the magnetic flux density we want to calculate. Omega is equal to, yes, 2 pi f. 2 times 22 over 7, and frequency is given in the problem 50 over 11. In this way, we managed to obtain the magnetic flux density. It is 0.38 Tesla. And now, how to convert from linear velocity into angular velocity? Yes, radius is given from, yes, width over 2. Width in the problem was mentioned. It is 30 centimeters, so 30 times 10 to the power 30 times 10 to the power of negative 2 over 2. It is 0.15. And since omega is equal to V over R, so omega equals the linear velocity 3 over 0.15. It is 20 rad per second. In this way, we can calculate the new maximum EMF. It is NAP, it is NAB omega, okay? Number of turns 300, area of coil 40 times 30 times 10 power negative 4, magnetic flux, we managed to obtain it, 0.38 times omega, which is 20. In this way, maximum EMF is equal to 280 volt. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.